Hello, I've made this alarm system design that I was using in PIC 16F887 and an Atmega 8 microcontroller. The PIC 16F887 was in the control panel, that's the white box here, and the Atmega 8 microcontroller was in the keypad, which is this box here. As you can see, I was demonstrating that the keypad is hot pluggable. You can actually plug it in, plug it out without affecting the operation of the control panel. And as you can see also that you can enter a code. It's a 4-key code keypad, and this keypad is actually a display and a communication entry point for the alarm system. It is using a UART communication link, as I have indicated on the video there. But then during my improvement of the product, I had a problem of the PIC 16F887 running out of resource, mainly the memory space, because I wanted to include the bypassing function, which is the stay function. Also, I realized that the PIC microcontroller had very few pins left for me to actually even improve on the product, so I had to look for an alternative. Right, I had an option of the Atmega 644, but then Atmega 644, although it has memory big enough to take the project, it was also not having enough resource on pins, the input and output pins. And I could also even go further to the Atmega 25, the Atmega 2560, I think, the other one, with the is it 100 pins? Okay, but well, as I normally do, my philosophy is to use electronic waste as much as possible. What I'm going to share with you is not the design of this project, but how I solved my problem with the microcontroller that I had chosen, or the microcontroller that I had access to. Right, I had these two boards that were lying around. I remember my Arduino concept that I started off in the previous video, the inverter. Right, the Arduino concept is you use boards with the components that you want, and you use as is. This board had actually an Stm32F100 VCT, which is a 100-pin microcontroller, and this one had an Stm32F745 IE, which is a 176-pin microcontroller, both from ST Microelectronics, and these boards were used for battery management system for telecom batteries, the lithium-ion batteries. So I took out the part that I didn't need, and I can show you on this part here that the board had, and the board was this piece together. These two pieces were together, so the board had actually this part here, which I actually just broke out, and the board actually is it's a 7-layer board. One thing good about STM microcontroller is this compatibility feature that they have across the family, meaning STM32F STM32F1 or STM32F2 or whatever family that you choose or that you have, you can actually write a code for one microcontroller and actually port it to the other with the minor changes. So when I discovered that, I gathered some tools to actually try out these microcontrollers. I had to download the Stm32Cube software, the IDE, and the STM32Cube MX configuration tool, and then started off trying out this microcontroller, reading about it, and then when I get to realize that these microcontrollers are actually software compatible to some extent, I was actually motivated to try out the ones that I had. So I had an STM32F100V, which is a 100-pin microcontroller, but ldmicro supports the STM32F103C8, which is a 48-pin microcontroller. The memory space and pin are obviously different, so I had to go around it and try out. So this is what I'm going to share with you. I can't write code in C, but I can actually do graphical programming, like using ldmicro, a nice piece of software, and I can also program using flow chart kind of programming, like a flow code. I've done some projects on my YouTube channel. You can check that. What I want to share with you is how you can actually code for one microcontroller and actually use that code on another, like what I did. So if you have any feedback or any comment, please, that's my email. You can actually email me. Thank you, and I hope you enjoy electronics. So to start off with, I'll start with the STM32F1 series project that I did using ldmicro, and ldmicro is a nice software, very powerful software, but it uses a ladder logic, like you are programming PLC. It's actually a PLC software, basically. Yeah, that's what it is, and it does wonders, and it does help people who can't write C or C++. I can at least now read a bit of C and adjust areas where I need to adjust. So ldmicro has got support for the STM32F103, but I have the STM32F100, so I wrote the program for it. You have a 100-pin, but you have support for a 48-pin. So the nice thing about microcontrollers is you actually address a port rather than a pin. This is the program for the alarm, so it basically looks like this, and I'm not going to share with you this one. What I'm going to share with you is, you see, this is STM32F10X, the 48-pin microcontroller, also called the blue pill. So I'm going to write a program for my 32F100. This is 103 basically, and 10 something, I think 105 or whichever, but it's a 48-pin version. I have a 100-pin version, so where I concentrate on is these ports. You write to the port. The PA10 for the 48-pin is on pin number 31, but for the 100-pin it will be different. It's not on this pin, it's on another pin, but still you have the PA10. So on the ports for the 100-pin, actually you have to select only the ones that are available on the 48-pin. So it was PA and PB ports only. because the 100 pin has got PC, it's got PD, I think up to PE. So I only use PA and PB, right? So this is how I did it. I wrote the program for the blue pill, and then when I did that, your ladder H file, your ladder header file comes out like this. Your ladder header file comes out like that, and the compiler that ldmicro recommends, the EMIDE, don't like this part here. It doesn't like this part here, so you have to actually remove this part, or you just comment it out and replace it with that one. I think I got them from the microchip XC8 compiler, that you actually have to use it here. I'll show you what happens if I compile and build C solution to get the X file. Right, elf to X, convert elf to X on the batch file. Right, on the batch file you have to right click. Right, okay, right click, edit. You have to edit the batch file. When you open the edit, you have to adjust this part here. This is my Windows 10 drive, right? This is my Windows 7 drive. So you'll see, you go into C, you go into program files, and then you look for EMIDE, which is this one, and then the EMID, you click again, you click again on ARM, and then you find this one, you right click, you go for properties, you copy that one. I'm going to close, and then when you go to the batch file, you will find that this is the path. That is the path, so it's in C, right? You must now save that batch file. Just save the batch file, and I should remember when I get to Windows 10 that I have actually changed the drive path. So right, I've changed that drive path now. Okay, it will give me another error. Right, okay, build C solution of what I've already compiled. So I build the C solution. Right, it should give me an error on the file types there. Right, okay, right, you see these are the errors that it will give you. And type define, attribute user lib, okay, no such file or directory. So I must remove user library. I must also remove another one, I think all those ones. So so it will not compile, you will not get the X file. Okay, so because it only gives an error and stops at the error, so I must adjust my ladder file. Right, this is the ladder file. So what it don't want is, it doesn't want all that. It doesn't want all that, so I must comment it out. I comment out these ones, remove that one, and then what should I do? I should copy. I copy ladder adjust here, copy that one, maybe even close if you want, and paste it here. I paste it here and save. Right, so I've excluded these guys here, this, and already these ones were excluded, but I have included the definition here, because these ones it don't like them. for some reason it don't like them. Okay, right, so I'm going to did I save? Okay, anyway, no problem. Save and close. Right, come back, close the batch file. Please do not compile GCC for that to be again, because it actually replaces the that ladder file, or replace the file with the changes that you have made. Do not compile again here, just build straight on, because if you compile again it will remove that adjusted file. Right, let's see. So now no errors. We now have the X file. Here it is. We now have the X file in the bin folder. If we go to our folder there, our project folder, we go into the GCC, we go into the bin. Here's our X file. To prove it, we go into our project folder, we delete this one, we delete that one. Right, deleted. Go to the file bin to be sure, empty the file bin, empty the file bin. Okay, nice. No GCC folder there. So we come back to our thing, we press any key, we go to our build, or you can just press F. So you see it copies those files back and creates that folder, GCC library. Okay, that's the batch file doing it, just to prove that it is doing it. So when you have that X file, you can load it to the microcontroller. But then I had problems with my microcontroller, because you remember my microcontroller is not the F103. It's not the Stm32F103. It's the Stm32F100. So yeah, right, here it is. Right, let me just close that one and show you again that that guy is back. You can see that guy is back with those files, the X file. This is the X file. Okay, this is the X file. Now again, the other thing was my microcontroller had enough memory for this, but because I am actually compiling it for the 32F103 with the less memory, 64 kilobytes, the program at some point could not allow me to actually improve on my design, like add analog to digital converter part of my design, and also include other things that I wanted. I had a limit, so that's why I had now problems with the STM32F1 series, because my program was a bit big for the 32F103, the blue pill. But then well, I was trying to work out something that actually would perform what I wanted to. So now we have this one, and okay, it's there, but the main problem was the configuration. Let me open the C file. You see where my problem was. You see here, these are the configurations for the microcontroller. Basically here it actually goes on the default setup, and there is no configuration for clock source and all that. So what I did was I had to actually put in some code here that I well worked out by myself, and these are the codes that I did. I just put in this code here from that point. This is what I did. Just copy this one. You can just copy this one like that, and you copy, close, and you go to here. It's actually, you place it here on the system initializing part. If I place it here, paste it here, I paste it here, you see that this part is already there, so I can actually take it out or take the top one, no problem, just delete that part. And this one is just to indicate that this is my edited part. So I actually here to adjust that part. I can save that one and then save the C file. Okay, no problem. And every other else is okay. The program will accept the setups and all that is already done, the pin setup and all that. Don't worry about them. UART setup is already done also, so just close that one, saved, and do not compile. Again, do not compile, please. If you compile, everything that you have done there will actually change to the normal, to the default. So you just build straight again. So those are the adjustments for the STM32F1000 microcontroller, and it was working until I did something that actually make the microcontroller didn't want, and it died. So I was back to square one again of having a problem with the fitting of the program into the microcontroller, until I had to actually adjust my program to a 10 zone system, and I was using the PIC 16F887 as a 10 zone without the analog sensing part. So you see it is actually compared to the X file, it's still there, so it's okay. You can take it out. So this is what I did, and I loaded that X file into the STM32F100, and it was working. Unfortunately, I do not have videos of it because I had not actually taken some clips of it working, and yeah, the circuit died before I could actually have information about it, or before I could actually collect videos of it. So this is what I did, and it was working. And this is the program for the alarm system. This is a 12-volt alarm system with a bypass circuit. I can just show you the bypass part. Yeah, this is the bypass. This is a stay circuit. So this part works, and it works very fine. And this is as far as I can share with you. Right. Then our next sharing will be on the STM32F745 microcontroller. Well, as you can see, ldmicro only supports on the ARM microcontrollers. It supports only these two microcontrollers. So somewhere within the documentation of ST Microelectronics PDF files, the reference files, they actually say the STM32F40 series is compatible in terms of binary setup, compatible to the STM32F7 series. No, this is what made me try out the STM32F7 series that I had on the board. I did write a program, the code using this microcontroller code working, and I succeeded. Albeit I removed the analog part because the UART part actually was as tiresome as I can imagine, and I know the analog part is just as much, because these microcontrollers are they're actually powerful. They do much more than what I want to do. There's more to it than what I can extract from them. So the rest of their capabilities is just a waste. Like this 745 microcontroller, well, much it's a computer. So I just extract what I needed, and because I have it, and I have actually 2 boards of it, I will use it for the alarm system. It's a tiny fraction of what it can do. I think maybe even less than 10% of it. I have actually taken less than 10% of the memory for my project. So this is what is there. I use this program because I like it. It's easy for me. I've been programming the POCs, so I have experience of POCs. This is how you program POCs. I can use function block, I can use graphical, I can use flowcharts, but I can't do C or any other high-level languages. I can only do graphical. So I'll use this one to code for the 7 series, and I will share with you what I did. Right, so for now, let's break and then see how I can approach it, the other part. Thank you. Till meet again. Right, I'm going to be showing you how I program this microcontroller, the Stm32F745, using this PC here, the serial port, using the serial port. Right, this is the programmer interface that I built, and this is the serial port connection for programming, and I'm going to actually connect it to the computer here. Okay, on the serial port. Right. Okay. After that, here is the boot 0 connection. I put it to the VDD supply here. Okay, I put it here. That's the VDD pin there. Okay, right. And this box, this mesh box here, has got the UART interface for the keypad. Okay, that's the UART interface for the keypad. This connector here. This connector here is the UART interface for the keypad. As you can see, just 4 wires. The red, green, the red and green is the supply power, and then the yellow and orange is actually the transmit and the receive wire. So just 4 wires. Okay, just 4 wires. And here is the power supply for the board. Power supply cable for the board. Okay, this is the power supply cable for the board. Red and black. Right. So I'm going to connect it, and then I'll show you what's happening. Right. When you power the board and it goes into boot mode, remember there is an LED that was flashing here. That LED, if it's in boot mode, that LED won't be flashing because the board is waiting for programming. It doesn't run the program that is loaded into the microcontroller. So yeah, now the board is in boot mode, so it's ready for programming. So let's go and see how I do it. I'll just show you the interface for programming this board. Okay. Right. As you can see, I'm using Windows XP, and yeah, that's Windows XP. Right, and my program is in this file. Yeah. Remember that hex file, Stm32 F7 alarm BP hex. So that's the file that is loaded into the microcontroller. Okay. Right, so what I do is I launch the demonstrator graphical user interface here. This software you can download from ST website. I launch it. Okay, double click. There it is. It launches. This is a UART programming interface. So it uses communication port number 1. And this is the baud rate it is using, and then all other settings, parity, odd, echo, disabled, and all that. And then you click next. If the microcontroller has been identified, is configured well, it will indicate. Right. Let me click. Right. Sorry, it skipped one stage. This stage here. If the microcontroller is actually connected properly, it will show you that one. This is target is readable. It confirms that the target has been seen. Please click next to proceed. Okay, right, you click next. Right, so it identifies the microcontroller, and then you click next. Click next to actually go for other settings. Well, I haven't programmed any option bytes for the microcontroller, so the option bytes are empty. I do is I have this file here that I need to load, the X file. Remember that X file that we generated using the Stm32Cube Ide. This is the file that we generated. I just ported to this PC from my laptop. Okay, so you can actually see the size of it. That's 124 kilobytes. Okay, right. And when you actually program the microcontroller, it will show you. If I click next here, it will start to write. Here I use the global erase. Now there is actually the Cube programmer interface that you can actually use, the tool that you can actually use to bend the microcontroller. The Cube programmer is only supported from Windows 7 upwards.